Hello, everyone. My name is David Burke, and I am from the Radio Raiders team of Wright State University. The goal of our project was to estimate the angle of arrival of a signal using a uniform linear array implemented by two SDRs. The estimation of a signal's arrival is even more crucial with the advances in wireless communication. Interference becomes a larger problem with more signals introduced. Knowing the angle of arrival can help fine-tune the receiver for limited interference and more efficiency. In this project, we take steps to learn as much as possible about the behavior of the SDRs, using techniques such as pulse modulation, match filtering, and the statistical analysis of a signal's magnitude and phase.
My name is Garrett Harris. I'm a second year master's degree student in electrical engineering with a focus on RF and microwave. I'm a Smart Scholarship recipient and I'll be working at AFRL STO once I finish my degree. And my project area is the algorithms and coding, experiment setup, and SDR configuration.
Hello, everyone. My name is David Burke. I am currently an undergraduate student going into my fourth year of a Bachelor of Science Electrical Engineering degree. My focus areas for my senior year include digital signal processing and communication, as well as VLSI. For the summer, I will be interning at Centauri as a technical intern, working with the Digital Signal Processing Group. My project areas for this project include software and algorithms, and SDR setup and configuration.
Hello everyone, and welcome to the experimental setup of the Radio Raiders team of Wright State University. Our first stop is the signal generator, in which we can see that we are transmitting a pulse modulated signal at 2.4501 GHz. We use 2.4501 to offset the frequency 100 kHz from our defined center frequency of our SDR. If we move into setup and go to modulation, we can see that we have a pulse modulation setup with a pulse period of 300 microseconds and a pulse width of 100 microseconds. The signal is fed through a coaxial cable into the pedestal with the antenna attached. This antenna is rated for 2.45 GHz and transmits the signal across the room into our SDRs. Our SDRs use 4 collective antennas to collect the data. The SDRs are connected to our laptop with GNU Radio installed. GNU Radio collects 20,000 samples of that data and writes them into a binary file. The binary file is then exported into MATLAB, and if we run our MATLAB code, we can see that MATLAB plots the data and lets us do our analysis from there.
So the goal of this project was to perform an angle estimation using a uniform linear array, which was fed by SDRs. So the way that we do this is we start by modeling the array like this. So this is a two-dimensional representation of it. And each one of these little patches down here are array elements. So when we have an incoming wave and it arrives off boresight, the phase at each element is a little bit different. It increases incrementally according to the direction of the wave, the frequency of the wave, and also the spacing between the elements. So what we can do is take the individual output of each one of these antennas and put it in a vector, which we'll call S. So S is a single snapshot in time. It takes the in-phase and quadrature data coming off of each one of your antenna elements. So you end up with something that is nx, which is the number of antenna elements you have, by 1. So we take that, and the way that we estimate the angle is we use a weight matrix. And the weight matrix is essentially the same format as the signal model, except what we do is we create a whole bunch of different weight vectors with different data and fees which lets us kind of test out different incidence angles and see what works. So since we have a weight matrix, which is the same form as the signal matrix, we can take the Hermitian transpose of it, which takes the complex conjugate of all of the complex values, and we use that, we multiply that by our signal matrix, and essentially the magnitude of those values will be the greatest when there's a maximum amount of coherence between the weight vector, the guess, and the incoming signal. So essentially we can just plot the magnitude of all those multiplications and see where the signal is coming from. So this is an example code that demonstrates how the angle of arrival algorithm works. Essentially what we do is define our hypothetical array. We give it the operating frequency, the wavelength, element spacing, and the number of array elements. And this code creates a pretend signal that will be the input to our array. And then we define a weight matrix, which scans across all the possible azimuth angles that the signal could be coming from. And then we plot the absolute value of that, the multiplication of the weight matrix by the signal matrix, so our complete scan, and gives us a nice little plot to show where the signal is coming from the strongest. So if we go up here and we define our signal azimuth angle as 15 degrees, and we go ahead and run it, then we get this nice little plot, and the maximum comes out at 15 degrees here. And you can also see that it outputs that our estimated angle is 15 degrees. So since the output of the SDR isn't a single value, it's actually a time series, and it also contains a good deal of noise. One of the ways that we've tried to increase the accuracy of our angle of arrival estimation is the use of a match filter. So this code here basically defines our match filter and gives a little example of how it would work. So if we look at the plots that we generate, in this figure we have a close-up of one of the pulses that we would expect. So our signal of interest is a pulse modulated waveform, and the top part of the figure here is just a close-up of one of those pulses. So this is what the perfect expected signal would look like without any noise, and it comes in with a random amplitude and phase. And then this plot down here shows what the actual SDR output would look like with noise, and it's just a little bit imperfect, as you can see. So the next plot here shows what the match filter looks like. So our match filter is perfect. It's got, it comes in with 0 initial phase, and there's no noise in it. And here at the bottom is what the output of the match filter would look like. So we take our input signal, the received signal from the SDR, and we convolve it with our perfect signal, our expected signal, which is the match filter. And on the bottom we get an output which gives us a measure of correlation between the expected signal and the received signal. So what we're going to do essentially, what we can do is sample the received signal at these points where this triangle is at a maximum, because that shows us where there's a maximum amount of correlation between the input signal and the expected signal. So in this way we can get the maximum amount of information about the timing of the signal and the phase of the signal. In this example, we're going to be taking in data made in GNU Radio, importing it into MATLAB, performing a match filter on it, plotting what the data looks like after match filtering, and then performing an angle estimation, and plotting what the coherence looks like when the algorithm is scanned across incidence angles from -90 to 90 degrees. So in this case we're looking at a set of data that was collected. We have 5 runs, and it was collected at an incidence angle of 0 degrees. So if we go ahead and run the code, this first plot here shows what the data look like at the first run. So this is a time series set of data, and this is after the filtering. The green triangles represent the coherence of the incoming signal with the expected signal, which is the match filter. And what we've done in this situation is we take the first peak of the first full triangle, and we use that data point there as the input to our angle estimation. So if we go over to our other plot, we've taken that point and we've compared it to scan angles from -90 to 90 degrees, and we found that the highest coherence is, on average, right around 0 degrees. So when we look at the average predicted angle across 5 runs, we get the angle estimate of 0.4 degrees right here.
In conclusion, this project was a success despite some inaccurate results. Most students do not have any experience with SDRs. This project helped gain experience even through some hardships. GNU radio was something none of us had probably used before, so it was good to get a basis of knowledge in that. We also were able to implement engineering techniques such as match filtering and understand the statistical analysis behind how the SDR works. We learned more about a Linux system and how to download, run, and configure GNU radio at MATLAB. We learned how to implement signal processing into a real-time transmission and reception. We learned more about IQ data and its relation to a signal's magnitude and phase. We learned how to effectively troubleshoot our code, SDRs, or GNU Radio Companion software. We discovered how using multiple SDRs can become a problem if not properly corrected. We discovered more about the SDR specifications, including the sample rate difference when connected to USB 2.0 and USB 3.0. We discovered that some software, such as MATLAB, can be used with the SDRs, but is not the ideal option. There are many challenges in this experiment, including COVID-19, lack of team members, and even driver downloads for the SDR that hindered our progress and results. Our team worked as much as possible, despite these obstacles, even reaching out to NS support for some installation help. In conclusion, the factors that could have affected our results include multipath bounce, issues or incorrect assumptions in our algorithm, a sampling rate that was too low to measure RF signals, or desynchronous SDRs. In the future, we would like to try this experiment again in a more open space with synchronized SDRs and possibly higher frequencies. Eventually, we may be able to expand into a two-dimensional array with more antennas and a better angle estimation.